This is the Walking Talking mock for Combined Science Physics Foundation. As we go through this, make as many notes as possible. I will explain my thought process. At times I will give you extra information and extra notes above and beyond the mark scheme to really help you understand how to answer not just these questions, but similar questions. So we'll start with the first question in the paper. Alex is cycling up a hill as shown in the diagram. The mass of Alex and the bicycle is 95 kilograms. At the top of the hill, the gravitational potential energy store of Alex and the bicycle has increased by 7,600 joules. So as you increase your height, gravitational potential energy also increases. If he was to decrease his height, that gravitational potential energy would decrease. So calculate the height at the top of the hill. It says use the equation gravitational potential energy equals mass times gravitational field strength times height. Now they've given you the equation here, which is great. If they hadn't given you the equation, what would you do? Well, I would go through the question and I would think, right, I've been given this is mass. I've been given this, J stands for joules, which is energy. And I also want the height, which is obviously height. So then I would look on the equation sheet, which you are given this year, and I would find the equation that has these things in, and you see it's this. Now there is this other term here, gravitational field strength, which they've told you is 10. You are expected to remember that, but sometimes they do give it. So how would we answer this question? Well, I'm going to write the equation out again, but in symbol form. So gravitational potential energy is E, or you could also write this, is M times gravitational field strength times height. So use these symbols. And it says calculate the height. So at this point, I'm going to put the numbers in, and then it's going to be a lot easier to find the height. So the energy is 7,600. The mass is 95. G is 10. And the height is what we're trying to work out. So that's quite easy to make progress on. We can obviously do 95 times 10, which is 950, times height. We now want to make height the subject of the equation, so we need to do the inverse of multiply by 950, which is divide by 950. So our calculation to find out height becomes 7,600 divided by 950, which is the height. And if I just quickly put that in my calculator, I get 8. So I'm going to write 8 on the answer line. Part 2. Alex transfers 9,000 joules of energy to reach the top of the hill. Explain why the amount of energy transferred by Alex is different to the increase in the gravitational potential energy store. So the increase in the GPE, and I'm just going to write this down just so I keep track of it. The increase in GPE is 7,600 joules, and Alex transfers 9,000 joules. So you don't need to do this, but it is useful just to keep track of the numbers. So what is going on when Alex transfers energy? Well, he is starting with a chemical energy store. So that is the chemical store in his muscles. And as he moves up the hill, he's transferring that into GPE. But when he or anybody is doing exercise, what also happens? Your muscles heat up and some energy is wasted as the thermal energy store. So what I would say is some energy is wasted by heating the thermal store of the surroundings, and that is basically your muscles. And what else? Well, we're pedaling, there's going to be friction in the gears, there's going to be friction in the pedal itself, so it's not just thermal plus energy wasted against friction. So in order to get more marks, I would, and this is obviously 3 marks, we've got to be, write a lot, and some energy is wasted due to work done against friction. So why have I put this word work done here? Work done means you're doing something, you're having to overcome another force, and that case, and in this case, the force is friction. Where is this energy also going? Well, this is also going into the thermal energy store as well. So we could add that in as well. Some energy is wasted due to work done against friction. This also goes to the thermal store of the surroundings. And hopefully that is enough for 3 marks. Okay, part 3, calculate the efficiency of Alex to get to the top of the hill. Well, you should always look on the formula sheet and you see that efficiency is useful energy divided by total energy. So the useful energy, we're trying to get high, and as we go high, we're increasing the gravitational potential energy store. So the useful energy is this 7,600. So it is useful sometimes to write these things out again because we keep track of them. The total energy was 9,000. So we can put that in our calculator. 7,600 divided by 9,000 equals, always as a number, 0.84. And that is perfectly fine to give us an answer, but we could also say it's 0.84 times 100 gives us 84%. Either of those is fine for efficiency, either a decimal or a percentage. You'll notice there's no units because the joules cancels with the joules, so there's no overall unit. Okay, B. Alex goes back down the hill without pedalling. Calculate the maximum speed that Alex can reach. Assume that no energy is lost going back down the hill. So we're assuming there's no air resistance, and we're assuming there is no friction. So that's obviously not true, but they've told us to ignore it, so we can. Use the equation kinetic energy, so that's E is 0.5 times m times speed squared. I'm going to write V there. Give your answer to 1 decimal place. That's quite important, so I'm going to highlight that. So the kinetic energy, let's look, which one do we need to use? So the 9,000 is how much heat transferred, but some of that was wasted as heat and friction, so we don't want to use the 9,000. We need to figure out how much GP he actually gained, and that was the 7,600. So the increase in energy, 7,600, equals 0.5 times the mass. So the mass was 95 times the speed squared. Squared is really important. A lot of people miss out the squared. So now I'm going to do my next step. I'm going to say 7,600 is 0.5 times 95. Oops, I did divide. So I'm always going to double check my calculations because it's so easy to make a mistake. So that's 47.5 times by V squared. I need to do the inverse of times. So I'm going to divide by 47.5 because I want to make V squared the subject of the equation. So V squared is 7,600 divided by 47.5, which is 160. And then I need to make V the subject, not V squared. So I need to do the inverse of squared, which is square rooted. So the square root of 160 equals 12.64 blah blah blah, but it said 1 decimal place, so 12.6 meters per second. Okay, question 9. So this looks like a complicated question, but it is going to be more simple than it might look. So what I'm going to do for long questions like this, I'm going to quickly look at the question and I'm going to read through all of the information to see what I actually need. So the question says calculate the power output when the current is 2 amps. So we want the power when the current is 2 amps, and it says use the equation power is work done divided by time. So I'm looking for something to do with power, I'm looking for something to do with current is 2 amps. So what's going on here? Kai uses the apparatus shown in the diagram to investigate the efficiency of an electric motor. So we've got a power supply, an ammeter measures current, a motor which is obviously going to turn and lift this weight up. Newton is the unit of force, so it is correct to say a weight here. When Kai switches on the power supply, the motor lifts a 50 Newton weight. He records the current on the ammeter, measures the height reached by the weight in 10 seconds, and then Kai adjusts the power supply and repeats his measurements, and we've got a table. So we're looking for the current of 2 amps, and we are using this equation, power is work done divided by time. So we've got this information, height reached by the 50 Newton weight is 2.30, and remember this is in 10 seconds. So the work done equals the energy transferred. All right, that's just what it means, and we're lifting it up, so that's going to equal the gravitational potential energy. All right, so similar to this question on the previous side, as we go higher, we're increasing the gravitational potential energy store. And we've got the equation here, it's also on the formula sheet. So this question is a bit sneaky. It seems like it's really tricky, it seems like you haven't got this, but it is just going back to that same basic idea of question 1. All right, just a little bit harder because they're asking you to do one extra step yourself. So GPE is M times G times H, and we've got mg, mass times gravity. So we've already been given this effectively because we've been given the weight. Mg does equal weight. So we've got 50 newtons times the height, which is 2.30, equals the gravitational potential energy, which is 115 joules. And then it's a really easy case of going power is 115 joules divided by time, which is 10 seconds, which is 11.5 watts. Is this answer sensible? Well, let's look. The power is increasing each time. It's also increased. There's a good chance that this is the correct answer. Now, if this was too complicated, there is one other way to think about this question. So I've picked this question just, because it is a good question. So there is another equation on the formula sheet. Work done equals force times distance. So it might be when you were looking at this question, you thought, hang on a second, we've got a force and we've got a distance. So why can't we just use this equation? And absolutely we can. We can do 50 newtons multiplied by 2.30, which obviously gives us 115 joules. And it is obviously the same as this. We've done exactly the same thing. Our weight is the force, weight is mass times gravity. So it's two ways to get to the same answer. Okay, plot the power output against the current on the graph. So, should be a really easy question. We just have to make sure we are, don't make any silly mistakes. So power output, the first power is 0, the current is 0, so I'm going to put my X on 0, 0. The next current is 0.5, and the next power output is 6.2, so 6, this would be, we've got 5 boxes, and that is going to be a difference of 2 watts. So one box is 0.4, which means half a box is 0.2. So you should use a sharp pencil to do this. So if you make a mistake, you can rub it out and put it in the correct place. We've got a current of 1 and 9.5. So 9.5 is going to be exactly in the middle. We've got 1.5 and 11.2. So that's 11.2. So I've made a mistake, haven't I? Because halfway between, I just said is 11. But over here, this would be 9. And it was asking me for 9.5. So this one is a mistake. So I've got to cross this out now. And because I've done it in pen, it's messy, right? This is why you always use pencil. So this is 9.2. 9.4, 9.6, so it's there. Now, you always get half a square of leniency, so if you're not entirely sure where it should be, don't worry, you get half a square. And then finally 2 amps and 11.5, this is 11, 11.2, 11.4, again 11.5 here. And you can see, actually this does not look like a straight line. A straight line would go like this. This is not a straight line. So if we had to draw a line of best fit, it would actually be a curve of best fit. So it's going to be a nice smooth curve of best fit. And the best way to do that is like I've done. You go underneath and you use the fact that your wrist will naturally make a curve. Okay, part B. Kai made a hypothesis before recording his results. When the current is increased in equal amounts, the power input also increases in equal amounts. Therefore, the power output should also increase in equal amounts. So what this is kind of saying is when the current increases, the power increases at the same rate. So he's kind of saying that the current is directly proportional to the power. So what he's trying to say is that the current and the power are directly proportional. And directly proportional means a straight line through the origin. So immediately, actually, that doesn't look true, does it? It doesn't look like it's a straight line through the origin. So what other quantity would need to be measured to confirm this hypothesis? So have a look at the table. When you have a look at the table, you can see we've been given power output, but we've not been given power input. So how can we answer this question unless we know what the power input is? So the quantity we need is the power input. So this is missing from the table. So we cannot see if the input power goes up in equal amounts. Because we do not know this or the total power. If we knew the total power, that would also be fine, because we could work out the input power. We don't know either of these. So how can we just can't work anything out. Right, part C, write a conclusion that Kai can make about the electric motor. Use data from the graph to support your answer. So what we can do is talk about how these two things link together. And we've already said it's a curve not a straight line. So we could say something like, as current increases, so I'm just literally saying, you know, what this is, as this increases, what happens to this? Well, as this gets bigger, this also gets bigger. So that would make sense. As current increases, power output increases. I'm just going to check how many marks it is. It's 2 marks. This is probably only worth 1 mark. So how could we add some more detail to this? Well, we could say it's not directly proportional. That will be one thing. Or we could be a bit more positive, and we could try and describe this in more detail. So if you can't think in an exam, you know, say it's not directly proportional. But if you are confident, then we can add a bit more detail. So we could say what is happening at the start. The current increases really, the power output increases rapidly, but then the power output is leveling off to a fixed value. So we could say initially, so at the start, the output power increases rapidly, but at higher currents, the output power, we could say levels off, or doesn't increase as quickly. Doesn't increase as quickly. So what we're saying is initially it's increasing really quickly, but then the rate of increase slows down and it appears to level off to a value. So different types of wave, or probably should say wave, shouldn't it, can be used for communications. 50 years ago, microwaves were used for long distance communications. Microwaves travel through the air between microwave aerials. Now, light waves travelling along optical fibres are normally used instead. Now, don't worry about optical fibres too much. If you know what they are, great. If you don't worry, you do not need it for this question. Compare and contrast microwaves and light waves. So it's 2 marks, so you want to say at least 2 things. Compare and contrast. So compare probably means what is similar. It can mean what's different, but contrast definitely means what is different. So what could we say that they are, what is similar? We could say they are both electromagnetic waves. So they are both on the electromagnetic spectrum. That also means they are both transverse. They can both travel through a vacuum. But what is different? Well, they have different frequencies, different wavelengths, and different energies. So what is different? We could say that microwaves have a longer wavelength, or that could also be a higher frequency. Or a I made a mistake here. What I meant to say was lower frequency. If it's a longer wavelength or a higher wavelength, it's a lower frequency, or a lower energy. And there's one other thing we could say. They are both electromagnetic waves, so that also means they both travel at 3 times 10 to the 8 meters per second, because all EM waves travel at 3 times 10 to the 8 meters per second. Now, it's only 2 marks. You do not need to write all of this. These 2 things would be plenty, but there's lots of other facts for your information. Okay, B. The table shows information about these waves, how it works. So microwaves and light waves, speed of the wave, time to travel. So what I've already written here is really useful, because here they've deliberately left a blank which you might think is that, but actually it's not that. That would be too easy, wouldn't it? All right, we're trying to find this out, and it's in an optical fibre. So when light waves travel in different materials, they speed up or slow down. That's refraction. So we need to use some information. We've been given the speed, we've been given the time, and we've been given a distance, haven't we? Time to travel 90 kilometers. So the speed is what we're trying to work out. The time for a light wave is 450 microseconds, and the distance is 90 kilometers. So this is 4 marks. So this is quite a hard question. All right, but this is why I've picked it. So there's a couple of tricks here. 90 kilometers is 90,000 meters, because kilo means 10 to the 3. And micro here means 10 to the minus 6. It's micro. So you often see this in biology when you're looking at microscopes, you're looking at magnification. You do need to remember that. So this here is 450 times 10 to the minus 6 seconds. Using the data sheet, so looking at the formula sheet, what links these equations? Obviously speed equals distance over time. So our distance is 90,000 meters, or 90 times 10 to the 3. Our time is 450 times 10 to the minus 6 seconds. So let's work out our speed. This time I'm going to use the fraction button, just so I get all the prefixes and things correct. 90,000, 450 times 10 to the minus 6. Press equals. Oh, that's a really big number. So I could copy it out. 1, 2, 3, 1, 2, 3, 1, 2. That's quite a lot. I'm going to count the zeros and write it in standard form. 1, 2, 3, 4, 5, 6, 7, 8. 2 times 10 to the 8 meters per second. Is that roughly what this is? They're both 10 to the 8. That is probably a sensible number, because they're both close to the speed of light, which is 3 times 10 to the 8. Okay, part II. An engineer suggests using an optical fibre made using a new material. In this new material, light waves take 343 microseconds to travel 90 kilometers. Calculate the percentage decrease in the travel time for this new material. So even if you didn't know what microseconds were, even if the previous question caught you out, don't worry, you can still get these other questions correct. So if I write down what I know, the original time was 450. The new time is 432. What is the percentage decrease? So again, this is something you often do in biology when you're looking at, for example, osmosis. You're looking at how much water something takes up, or how much water something loses, and you're often asked to work out the percentage decrease in mass. In chemistry, again, you do this a lot. It's a really, really useful thing to practice. So what is the change in time? 450 minus 432, which is 18. So the percentage decrease is the change over the original times 100, because it's a percentage. So the change is 18. The original was 450. Multiply that up by 100. And we get our percentage decrease. So 18 over 450 times by 100 is 4%. The new material will be 10% more expensive than the old material. Suggest why it is not worth using the new material. Use your answer to part B, II. So it's asking you to compare this with this percentage. So What is our saving in time? 4%. So presumably we could send 4% more information, or we could get 4% quicker internet, but it costs 10%. So that's probably not a good saving, is it? It costs far more than we save. So the cost is 2.5 times, or you could just say a lot more than the saving. And it's only 1 mark, so that's probably enough. You know, if it was only 1% more expensive, but I saved 4%, well, that's great. That's a 4% return. That would be worth it. If it was 4% more expensive and I saved 4%, it'd be worth it, but it's not. It's far more expensive than I save. All right, D, we've got some simple statements, true or false. Infrared radiation is emitted from the nuclei of the atoms. That is false, because they're emitted from the electrons in the orbits. If the electrons move from one energy level to another, then they can emit EM waves. So that one is false. Visible light is generated when electrons and atoms lose energy. Well, that's what I've just said. That's true. X-rays have enough energy to ionize some atoms. That is true. What's ionizing? We've got ultraviolet is ionizing, X-rays or gamma are all ionizing. Radio waves are absorbed by oxygen in the atmosphere to produce ozone. That is false. That one actually, I wouldn't worry too much about. That's not something that will come up on your exam. I think this one question I used was on a different exam board. But that is false. It's ultraviolet. Okay, question 5 was very similar to a previous question, so I'm not going to do that. I'm going to let you complete that after we finish this. We're going to move on to question 8. So we've got Eve investigates the reflection of white light from a mirror. So this symbol here, if you see this symbol, that means mirror. That's just the symbol we use. Describe a method to record the path of the ray of light shown in figure 8.1. So we've got the ray box. So inside this is a light bulb, and then it produces a ray of white light, and we want to record the path of the light shown. So it's a method. So what I would do is, using a sharp pencil, put 3 X's on the light ray, remove, actually I probably don't even need to remove the equipment because it looks like it's quite big, and then I would join up using a ruler. So I would put an X here, an X here, an X here, and then I would get myself a ruler and I would join up those points. So it is simple. Sometimes these simple questions catch people out. I think, oh, it must be really difficult. It's a GCSE question. Actually, it is describing a very simple method. What would you literally do in class to be able to record or trace this light ray? Part B. Complete figure 8.2 to show the ray of light reflected from the mirror. So we've got to remember for reflection that the angle of incidence equals the angle of reflection. So whatever angle it comes in at, it has to rebound, it has to bounce off, it has to reflect at that same angle. So if you have a protractor, great. If you don't, you can usually do it by eye, and that's usually acceptable. So I've just done that by eye, and I've used well, I should have used an actual ruler, but I've used effectively a ruler there. And that is close enough. Now, if you want to, you can add in this dotted line. This dotted line is the normal. Sometimes they ask you to put that in this one they haven't. And we could label, if we wanted to, the angle of incidence. It's always the angle between the normal and the ray of light, and we could label the angle of reflection, again the angle between the ray of light and the normal. In this question I don't think that you had to, but it's always worth doing. Part C. Eve wants to investigate whether infrared radiation reflects from a mirror at the same angle as visible light. Suggest how she can produce and detect infrared radiation to complete this investigation. So a slightly unusual question, one that's kind of designed to catch you out. How can we produce infrared radiation? Well, we need to remember that anything that is hot gives out infrared radiation. So use a hot object, e.g. a beaker of boiling water, to emit infrared light. And how do we detect it? Well, you can't detect it with your eyes, you can't see it, but you can use thermal imaging cameras, which give you the colours of hot objects, where you see like something that's really hot as red, something that's quite warm as maybe yellow or orange, something that's cold as blue. That would show us where the infrared radiation is. So use a thermal imaging camera to detect the radiation. Now, would this be the best method? Probably not, because if you had a beaker of water, that infrared is going to go in every single direction, so that might not give you good results. So if we wanted to do this, use a hot object, e.g. a beaker of boiling water, to emit infrared light. We would also use something that blocks infrared radiation. So for example, plastic sheets to form a thin ray. So rather than like when you use a ray box, you always pass the light through a very thin slit. If you use something that blocks infrared, you could do the same thing and you get a thin beam of infrared. Or there's probably an even easier method for this. So this is, to me, was the most obvious one. All right, and you should always do what's the most obvious. But actually there's probably a better one, which is use a remote control. Because a remote control will shine out a beam of infrared light, and it will already be in a beam. So we could put a remote control here, shine out the infrared light, and then we could put our thermal imaging camera here and see if it's detecting it at the same angle. So use a remote control would, I think, be the best one here. Okay, part I here is a complete mistake. Cross this one out. This just should have been deleted. Okay, oh no, that's that question done. So the final question we will look at is this one to do with radiation. So Alex works as a technician at a medical equipment manufacturer. He uses cesium-137 to calibrate radiotherapy equipment. So what is radiotherapy equipment? This is like medical equipment probably to treat cancer. Cesium-137 emits beta and gamma radiation when it decays. The graph shows how the activity of a sample of cesium-137 is expected to change over 50 years. So activity is the number of radioactive atoms decaying per second. It's always useful to remember that, and it has this unit BQ, and BQ stands for becquerels, which means per second, which means 1 every second. Use the graph to find the half-life of cesium-137. So half-life is the time it takes for the activity to halve. So what do? I started at 80, half of 80 is 40, and I want to know how long it takes to get from 80 to 40. So I'm going to get a ruler, I'm going to draw a line across on my graph, and then I'm going to draw a line down, and this time here is my half-life. So I can see that it is 26, 7, 8, 29 years. Why is cesium-137 dangerous? So let's go back to our information. It emits beta and gamma. So beta and gamma radiation are ionizing. Alright, you should always put this word in when you see the word danger. They always want to see this word ionizing. This means they can kill cells, or you could say mutate DNA, leading to an increased risk of cancer. So we always want ionizing, we want something about killing cells or damaging DNA, and something about increased risk of cancer. Always, always, always when you see radiation danger, this is the answer. Okay, Alex considers the best way to dispose of cesium-137. We should dispose of the waste cesium-137 in landfill with normal waste. It will be safe within 100 years. Evaluate Alex's statement. So is it sensible that it will be safe within 100 years? Should we put it in landfill? So with all our regular waste. So I'm going to do the 100 years first, and then we'll come back to the landfill. So after 50 years, actually, no, I'm not going to start with 50 years. I'm going to start with this 29 years. So after 29 years, it is halved. So let's just pretend that's 30. So after 30 years, we have half of what we started. At 0 years, we had everything. At 60 years, we've got a quarter. After 90 years, we've got an eighth. After 120, we've got a 16th. So is it true that after 100 years, which is here, there's nothing left? Well, actually, we've got quite a lot left. We've got roughly an eighth of what we started with, which is quite a lot, really. So I would say the half-life is 29 years. So after 100 years, there will still be a significant amount left. Now, if you did this calculation, great, you could add it in. If you didn't, I don't think it matters because there's only 2 marks. If it was 6 marks, absolutely I would expect this calculation. But for 2 marks, this is probably enough. And what else? So in landfill. So is it a good idea to put something that emits beta and gamma in landfill? So we need to think what blocks beta, what blocks gamma. So beta is blocked by meters of air or aluminium. Well, it's millimeters of aluminium. But gamma needs thick lead or thick concrete. So if you put it in landfill, which is a couple of meters down, maybe 5 meters if it's a big landfill tip, is beta going to get through? No. Is gamma going to get through? Yes, because you're not in landfill, it's not going to be kilometers underground, and you're not going to be putting lead or loads of concrete on top. You're just going to be putting more rubbish. So gamma can still penetrate the landfill and will be detected outside the landfill. So I'm just going to put not safe. I think that's fairly obvious, but sometimes it's worth just stating the obvious, that this is clearly not safe. Okay, question 4 is a similar one about waves, speed, distance, time. I'm going to let you do that one. Are there any more that I want to do with you? Right, we're going to do one final question on radiation. So if you could find this question, that's number 9, where it has this table and this equation. So it says complete the nuclear equation for the decay of the uranium isotope into an isotope of thorium. So we need to know what kind of radiation this is giving out. So we're going to look at our table. We're going to look at uranium, which is this one, and we see it's alpha emission. So it's going to go to thorium plus alpha. So we need to know what our numbers are. So if it was gamma, well, gamma has 0 mass and 0 charge. If it was beta, beta has close to 0 mass and -1 charge. Alpha is a helium nucleus, so it's 2 protons and 2 neutrons with a +2 charge. It's always 4, it's always 2. So I'm going to write these numbers here. And then I need to make my equation balance. So I've got 2 things to balance. I've got the mass number to balance. So how do I make the mass number balance? Well, what number needs to go here to make the left-hand side and the right-hand side the same? It must be 230, because 230 plus 4 is 234. And on the bottom, I need to make the atomic number balance. So I've got 92 and 2, so I must have 90 here. So supposing my question was carbon 6 decays, what does it decay into? They might give you this. How would you do this? So I would look at carbon, I would look at the fact it gives out beta, I would write in my numbers for beta, always 0 and -1, and then I would make the top numbers balance. So if 14 here, this is 0, this must be 14, this is 6, this is -1, so to make the right hand side balance, this must be 7, 7 minus 1 is 6. Okay, BI. A woolly mammoth was discovered in a melting glacier. The net decline of carbon-14 emission of the mammoth was recorded as a quarter. Calculate how long ago the woolly mammoth died. Used information from the table. So these questions are really easy if you use a very simple table method. So we want, in our table, half-life, fraction. Sometimes this is activity, sometimes this is mass, but in this case it's fraction, and we want the number of half-lives. So the number of half-lives is always going to start at 0, it's always going to go 1, 2, 3, 4 and so on. Half-life, actually it probably shouldn't be half-life, sorry, it should be time. So we're always going to start at 0 half-lives, we're always going to start at 0 time. After 1 half-life for carbon-14, we've got 5.73 times 10 to the 3. After 2 half-lives, we will have 2 lots of 5.73 times 10 to the 3. After 3 half-lives, we'll have 3 lots of this time, and so on. We'll have 4 times this. So let's look at our fraction. Well, what do we start with? We start with 1. After 1 half-life, it halves. After 2 half-lives, it halves again. So half of a half is a quarter. So really, we want this row here. We want 2 lots of this. So I'm going to type that in my calculator. 2 times 5.73 times 10 to the 3. And I see it's 11460 years ago. So just one reason why the value calculated in BI is likely to be inaccurate. So why is this not a perfect answer? So one obvious one is background radiation has not been, actually would it be this one? Because we're not really being asked about this. We're not really, nothing has been mentioned, and it just says we're measuring this. So usually this would be an answer, but I don't think this is correct. So I think I'm just going to go for my standard answer when we're talking about radiation. Radioactive decay is random, so the value will always vary slightly. Alright, if in doubt, if it's a bit harder, which is this one, you know, a little bit tricky, go for what's obvious, go for what's simple. Radioactive decay is random, so the value will always vary slightly. Okay, we're going to stop here, and there are plenty of extra questions in this pack for you to complete on your own.